good. I think this topic more than others is interesting. I don't know if you've done this before. I think it's pretty cool, right? So we're talking about relative motion, relative velocity. Everything we've been doing has been relative to Earth, which is moving, right? We're assuming our Earth's not moving, right? So when we say the projectile is going 40 meters per second, that it really is going 40 meters per second with respect to the ground, right? With respect to the Earth, okay? But what if we wanted to find or know or given the velocity of one thing relative to another thing that is moving, right? So, imagine we're driving down the interstate, right? The speed limit is 70 miles per hour, right? And in car A, that'd be Austin, right? Austin right here. Austin's in car A, and speed limit is 70 miles per hour. Austin, how fast do you fly down the interstate? Austin, how fast are you going down the interstate? 70? Yeah. All right, hey, following the rules. I like that. Following the rules. All right, so car A is going 70 miles per hour, right? Don't know why you're in the fast lane, going 70. I'm in the other lane. I like to go 79. I don't know if anybody else does that. Like, maybe I'm not really, not going to get a speeding ticket. All right, so listen, I'm going 79. So, Austin, I'm passing you in the slow lane. All right, but what do you think the velocity of my car relative to Austin, right? Not relative to Earth. Like, what if we just forgot about the road, forgot about the trees, just my car and his car? The velocity of B with respect to A. Velocity of Blake, right? My car. Velocity of B with respect to A would be what? Like, if he didn't know any better, if he didn't see the trees, if he didn't know how fast he was going, if he just saw me going by at 79, what would my relative velocity, my velocity relative to his be? 9. Yeah, it'd be 9. If we didn't know any better, it'd almost be like I was just going 9 miles per hour faster, right? And so that's relative velocity. So let's call this. So when we say B/A, this would be the velocity of B with respect to A. That's like if A was the center of the universe. If A was the reference, if A was the origin, then the velocity of B, not with respect to the Earth, but with respect to A, or relative to. So instead of respect to, we could say relative to velocity of B relative to A would be, can we write an equation with 70, 79? Would be VB minus VA, right? Because we said that 9 is equal to 79 minus 70. So if we have something like this, B/A, then that's VB minus VA. Okay? So that's VB minus VA. So let's kind of just rewrite this. B/A equals VB minus VA. Anybody kind of guess what VA/B would be equal to? VA minus VB, yes, it would be negative of VB/A. It's just one opposite directions. So you could kind of memorize that equation. But what if it's A/B? Then to make sure, be careful with these subscripts. Make sure you do VA minus VB. Hey, what if it's car/train? Then do V car minus V train. And look so here's one way to write it. Another way might be something like this. VB equals VA plus VB slash A. This is actually how I like to memorize it, and that's how the equation is on your formula sheet. Except I think the formula sheet probably says VA equals VB plus VA slash B. Those subscripts matter, and you kind of need to alternate. You can see here VB, you have VB on the left-hand side, then you've got A, then you've got B slash A. All right, so B, A, B slash A. Or if you started with A, B, A slash B. Or car, train, car slash train. You know? Right? So it's not always A and B. It's just two different things that are both going with some velocity. If you want to know the velocity of one relative to the other, you do it like this. A few things. This is true for vectors, right? When we're going down the intercept, we're kind of just thinking one direction, but this is true for vectors. Y'all know how I like to handle vectors. I kind of like to separate I from J. So it's almost like two equations. You know, my I equation and my J equation. So sometimes it's easy to keep them together. But just don't forget, it's two equations. So sometimes you can kind of solve for two unknowns. Maybe I don't know the direction of one of these velocities, and maybe I don't know the magnitude of one of these things. I can find direction and magnitude, those two unknowns, because I can look at the I equation and the J equation. Okay, these are, I like to think of these as real, right? This VB is the real velocity B. I'm really going 79 miles per hour, right? VA is the real. All right, Austin's really going 70. This VB slash A is not real. And when I say real, I'm talking about relative to Earth. But this 9 is perceived, right? It is perceived as if you think the world revolves around yourself, you know, you think you are the origin, then that would be the perceived. The relative velocity is kind of your perceived velocity. All right. Have y'all ever been in a car wash where you sit still, right? Not one of these new car washes that you do drive through, but a car wash that you sit still. I remember this when I was a kid. I don't know. Sit still, and the rollers start going backwards, and it kind of seems like you're moving. You know, it kind of seems like you're. It's almost like you perceive that you're moving forwards because we've been trained to think of our velocity relative to Earth, right? Relative to everything that's flying out, you know, everything outside of our windows. And so when you've got something covering your windows that's moving, you know, it moving backwards, it seems like you're going forward. That's kind of like this. The velocity of your car is 0. Let's see if I can do this. The velocity of your car is really 0. The velocity of those rollers, I'll say V subscript R, is, let's call it -1. So that's real. Your real velocity of your car is 0. The real velocity of the rollers is -1. Sometimes your perceived velocity would seem like you're going +1. This would be the velocity of you relative to the rollers outside your window. VC slash R would be +1. Does that fit into our equation? VC equals VR plus VC slash R. All right, I alternated these subscripts, C, R, C slash R. And does this mathematically make sense? 0 is equal to -1, +1. All right, have you ever been in a car that's parked and the car next to you is backing out? You feel for a second like you feel like you're going forward because something outside your window is backing out. It feels like you're going forward relative to everything outside your window. I think that's why, you know, some of these simulators are so effective, because we're used to getting our velocity relative to outside. And when the thing outside the window seems like it's moving, then we perceive like we're going. Another reason they're so effective is because forces give you acceleration. And so if you're not accelerating, doesn't it feel the same if you're in a car versus you're in an airplane? You'd be going completely different velocities. But if there's no acceleration, there aren't very many forces on you. So you just think you're going the speed of the things that are going outside your windshield. Okay. But anyway, I thought that was interesting. It's relative velocity, but again, this is real, right? Those velocities are real velocities. They're actually happening relative to Earth. This is perceived. Your relative, I think that C/R, your relative velocity is not relative to Earth. It's just velocity of the car relative to the rollers, C/R. Okay, so we could be talking about position or velocity or acceleration. Very similar, right? Position, velocity, or acceleration. We might want to know, hey, what's the relative position of A with respect to B? Something like that, okay? So let's look at point A. Its real position vector is that RA right there. Point B, its real position vector, here's point B right here. Its real position vector is that RB. But what is the position of A with respect to B? If you're B, and you think the world revolves around you, then you're like, okay, well, A is up and to the left, right? So this right here, this vector right here would be what? RA/B. Right? That would be the position of A with respect to B, or the position of A relative to B. All right, so what about that formula? Let's see. RA is equal to RB plus RA/B. Is that true? You can add vectors tip to tail, right? RB plus RA/B. That's the right-hand side of my equation. Yeah, it is the same. I would get to the same point right there. Okay. RA/B is from B to A. From B to A. So if you're going from B to A, that's RA/B. And this is real, but this relative term is perceived. Relative term is perceived. Okay, so relative velocity. We've been talking about this one. That would be velocity A/B, right? And is this true? VA equals VB plus VA/B. Yeah. So a few other things that are true. Let's see what other equations are true. Is VA/B equal to VA minus VB? That's a little harder to see, but yeah, it's true. Okay, so I would only use one of these equations, and you can just rearrange. Is this true? This would be a little bit harder to see maybe, but VB, VA, VB/A. Yeah, because VB/A would be in the opposite direction of VA/B. So it'd be something like this. I wouldn't draw this, but it'd be that. And so is this the same thing as VA plus? Yeah. So there are a few ways to write these equations. I would stick with, I like to stick with that one that's on our equation sheet and alternate those. So VA equals VB, let's be A/B. V car equals V train, let's be car/train. You know? Real perceived. This is the real velocity vector. This is the real velocity vector. This is the perceived velocity vector. And don't forget, these are vectors, so it's kind of two equations if you need to. We'll do one in a minute where I'm actually going to keep them together, but many times I like to kind of separate I equation and J equation. Two equations, I, J. Okay, and acceleration is true as well. How about this? That vector right there would be the acceleration of A slash B, A with respect to B. AA equals AB plus A slash B. All right, let me actually go back. I wrote quite a few equations that are true. These three equations are all true. And mathematically, I think you could see, but not everything is true, right? This right here, VA equals VB plus VB slash A would not be true. You know, don't just randomly put those subscripts in there. Be careful. All right, be careful. I would start with this one and then just rearrange if necessary. Okay, so anyway, acceleration of A equals acceleration B plus the acceleration of A with respect to B. Real, perceived. And I would caution you with this one to, let's see, don't forget normal acceleration. Don't forget normal acceleration if there's a circular path, right? Most of the time we think acceleration is speeding up, slowing down. If you notice that, hey, point A is in a circular path, then don't forget about A's tangential acceleration, speeding up, slowing down acceleration, but don't forget about A's normal acceleration, v squared over rho into the curve, right? Into the curve. All right, let's do some problems. Right? That'll be fun. No, oh, sorry. No, one more, sorry. I like this one. All right, so y'all are at the airport, right? They have those moving sidewalks sometimes, or I don't know, head to Universal Studios is when I remember. All right, so I'm walking let's say I'm going 3 miles per hour, and then I get on the moving sidewalk. I like to keep walking. I don't know about y'all. Sometimes some people just get on that and just stand there, start going. But I like to keep walking, right? So if I was going at 3 and I hop on a moving sidewalk that is going forward at 2, then how fast am I moving? So if the moving sidewalk is moving at 2 miles per hour and I was walking at 3 and I keep walking at 3, how fast am I really going? Not a trick question. Yeah, I'm really going at 5, right? Okay, so this fits into our relative velocity equation. What's our equation? Something like VA is equal to VB plus VA slash B. Okay, so when I'm on the moving sidewalk and my legs are still walking, okay, how do these 3 terms fit into these 3 terms of my equations, of this equation? Let's start with this one. Which one of these is going to be VA? It's got to equal VB plus VA slash B. 5. Yeah, that's got to be the 5 if the other 2 add up to it, right? So this is going to be the 5. All right, so which one of these is 3? Which one of these is 2? Any guesses? What do you think? Either. No, it matters. It matters. UV is 2. Yeah, so we got to vote for putting a 2 right here and a 3 right here. I would agree. There's a few different ways. But this, I like to think of real perceived. Right? I like to think of real perceived. Okay, right? I'm really going at 5 relative to Earth. Right, and the sidewalk really is moving forward at 2. But that 3, so what is that 3? That 3 is what my legs think they're doing, right? That 3 would be what I'm doing relative to the sidewalk. So if I put on blinders and was only looking at the sidewalk and was walking, wouldn't it seem like I'm only going 3? So I wanted to get at the relative term is the term that of, like what you think you're doing, right? What you think you're doing. Or maybe what you are doing if there was no moving sidewalk, right? What you're doing if there was no moving sidewalk. Okay, so right here, let's put, this is like the current. Whoops. This is like the current, like maybe a river. A river, like you're swimming, but the river is also taking you downstream. Maybe it's helping you go faster. Sometimes you might have to swim against the current. All right, vectors matter, right? Vectors matter. So this term right here would be the current. And so this term, and what's probably most important, is to make sure that bottom of that denominator, A/B, make sure that B is the current. Okay? Make sure that B is the current. The bottom of that A/B denominator, the subscript right there. Or if you do like I do and all you do, be A, be B, be A/B, put that current right there in that term, in that spot right there. Okay? Don't forget these are vectors. Okay, now